Oh my god, what are you using? That look refreshing.
Oh, this is toner that I use after cleansing.
Oh.
Yeah.
Do you know how it works or how the formula works with your skin?
I don't know. I just know it feels good on my skin.
I get that. But every skincare product, there's a little bit science in it.
Oh, is it?
Yeah. I explain to you how the science of chemistry work, especially acid-base and titration.
Wow, that's really amazing.
Yes, it helps us to understand the safety and the quality of products like your toner.
Wow, amazing.
Ready to dive in? Let's go!
Assalamualaikum and good day everyone. Today I will present the introduction of our experiment on acid-base titration in skincare toner. Acid-base titration is an analytical technique used to measure and control the acidity of skincare toners. This method helps determine important parameters such as pH, titrable acidity, and buffering capacity, which are essential for ensuring product quality and skin compatibility. In skincare formulations, acidic products are commonly designed to have a pH range of 4 to 6, which is close to the skin's natural pH. Maintaining this pH range helps support the skin barrier and promote healthy skin function. However, the effectiveness of a toner does not depend on pH alone. It is also influenced by concentration of acidic components, the overall formulation, composition, and the skin's natural buffering capacity. Therefore, acid-base titration is an important quality control method that helps ensure skincare toners are safe, stable, and effective for consumer use.
Now, let's get into the core theory behind this skincare formulation. First, we need to understand the chemistry of our product. We have acid, which are hydrogen ion toners. You will often find this in toner, typically as AHA or BHA, which is worked by gently exfoliating the skin. On the other side, we have bases, which are often found in soap-based cleanser for a deeper clean. Next, we look at the pH scale. It's our guide to balance. Remember, anything below 7 is acidic and above 7 is basic. But here is the most important part, the importance of maintaining pH equilibrium. Our skin thrives in a natural equilibrium zone between pH 4.5 and 5.5. Toner acts as a critical bridge to reset this balance immediately after cleansing and keeping our skin very healthy and protected. So it's not just about cleaning, it's about maintaining the perfect chemical harmony on your skin. So, how do we translate this theory into practice? We use titration to control and verify this pH level. It is the key to achieving the accuracy needed for safe skincare formulation. The most crucial process in this reaction is neutralization reaction, where an acid and a base react to form salt and water. This is our core principle for measuring the acidity or alkalinity of skincare product. To get precise result, we use the volumetric titration method. By using a buran and pipette and standard reagent like NaOH or HCl, we can calculate the exact concentration of active ingredient using the formula M1V1 equal to M2V2. Of course, we need to know when the reaction is finished, right? So, we use the indicator like phenolphthalein for a visual endpoint and verify the final pH with a pH meter or pH paper. Ultimately, this is about manufacturing importance. By performing this test, we ensure product safety, prevent skin irritation, and confirm that our toner met industry standard for ingredient stability and efficiency.
Our experiment has three main objectives. The first one is we use the acid-base titration method with sodium hydroxide as the titrant. Second, we measure the concentration of the active acidic ingredient in the toner. And the last one is we check whether the toner is safe for skin application by making sure its acidity level is within the acceptable range. Moving on to our methodology, I will explain the first procedure, which is part A, the preparation of sodium hydroxide solution and the standardization of sodium hydroxide. We begin by accurately weigh the solid sodium hydroxide inside a weighing bottle using an electronic balance. Next, the weighed sodium hydroxide is transferred into a beaker where we add distilled water and stir it thoroughly with a glass rod until the solids completely dissolve. Once it dissolves, the solution is carefully poured into a volumetric flask through a funnel. To ensure accuracy, we rinse the beaker and the glass rod with distilled water, transferring all the washing into the flask. Finally, we top up the volumetric flask with distilled water until it reaches the calibration mark, and then we invert it to mix the solution uniformly. Once our solution is ready, we set up our titration apparatus and fill the burette with our prepared sodium hydroxide base solution, making sure to record the initial volume reading. In the conical flask below, we have our acid solution mixed with a few drops of phenolphthalein as our indicator, which means the solution is completely colorless at this stage. During the titration, it is very important to continuously shake and mix the conical flask to ensure that the sodium hydroxide react completely and uniformly with the acid. Shaking the flask helps the solution achieve a proper chemical equilibrium and prevent the over-titration. We slow down the drops as we approach the expected endpoint, and the titration is stopped the exact moment we observe a permanent color change where the solution turns from colorless to light pink. Then, we record the final burette reading to calculate the exact molarity of our sodium hydroxide solution. Moving on to the next part, which is part B, the preparation of toner sample. First, we pipette exactly 10 mm of toner and transfer it carefully into a 100 mm volumetric flask. Next, we dilute the mixture to the calibration mark using distilled water, making sure to shake it well until it reaches a complete chemical equilibrium. After that, we transfer a 20 mm portion of this dilute toner solution into a 250 mm conical flask. Finally, we add 2 to 3 drops of phenolphthalein as our indicator to complete the sample preparation. Once the sample is prepared, we proceed to part C, which is the titration of the toner sample. We begin by filling the burette with our standardized sodium hydroxide solution. Then, we titrate the toner solution slowly while continuously swirling the flask until a light pink color appears and persists for at least 30 seconds. Then, we record both the initial and final burette reading at this exact endpoint. To ensure accuracy and reliability, we repeat this entire process for 2 more titration to obtain at least 3 consistent readings. Finally, we record all our data in the data table.
Next, I will explain the example of the titration result. So in this experiment, a 10 ml toner sample was titrated using the 0.1 molar sodium hydroxide with phenolphthalein as the indicator. So 3 titration trials were carried out to obtain consistent result. So the volume of sodium hydroxide used were 12.4 ml, 12.5 ml, and 12.6 ml. The average volume of sodium hydroxide used was calculated to be 12.5 ml. So, this average value will then be used in the next step to calculate the concentration of the acidic component in the toner. Now, I will explain the calculation of the molar concentration of glycolic acid in the skincare toner. So first, the balanced chemical equation for this reaction is glycolic acid react with the sodium hydroxide to produce sodium glycolate and water. So from the balanced chemical equation, 1 mole of the glycolic acid react with 1 mole of the sodium hydroxide. So, mole ratio between the acid and base is 1:1, which is mean the value of A and B is equal to 1. So, to calculate the molar concentration of glycolic acid, we use the titration equation, which is the MABA divided with MBVB equal to A over B. So, we substitute the value obtained from the titration. So the concentration of sodium hydroxide MB is 0.1 molar. The volume of the toner sample VA is 10 ml and the average volume of sodium hydroxide VB is 12.5 ml. So we rearrange the equation to solve for MA, which is the molar concentration of glycolic acid. So, after the calculation, the molar concentration of glycolic acid in the toner sample is 0.125 molar. Now that we have calculated the concentration of glycolic acid, let's see how this analytical method is applied in real life. So, one real-life application of acid-base titration is in cosmetic manufacturing, where it used as a part of the quality control process. So, it helps determine the concentration of acidic ingredients in skincare product and verify that the product meets the label specification. In addition, it ensures consistent quality between the manufacturing batch and support product safety and effectiveness before the product are released to the customer. So one example of application is glycolic acid. So glycolic acid is the active ingredient in exfoliate toner. So during manufacturing, acid-base titration can be used to determine the concentration of glycolic acid. So the measured concentration is then compared with the product specification to ensure that the toner meets the required quality standards before it is marketed. So this is important because it helps ensure consistent quality in every batch, reduce the risk of incorrect acid concentration, and increase consumer confidence in the product.
In conclusion, this project successfully used acid-base titration to analyze the chemical properties in a commercial skincare. By neutralizing the toner with a standardized sodium hydroxide solution, we determined that the concentration of citric acid in the product is 0.0192 molarity. Knowing this exact concentration is important for both safety and effectiveness, since the skin natural pH is slightly acidic between 4.5 and 5.5. Skincare product must be carefully formulated. This experiment confirms that the toner acidity is safely controlled to work with the skin natural balance without causing any irritation or barrier damage. Ultimately, this demonstrates how precise chemical analysis and quantity of control ensure that the skincare product we use every day are both safe and effective.
Wow, now we finally understand. Remember how confused we were at the beginning? It is out. Toner isn't just random liquid.
Yes, it's actually a perfect acid-base titration in a bottle. That science experiment is exactly what keeps our skin safe and balanced.
I know, right? No burning, no irritation, just a pure chemistry with our skin. So, science is really the secret for our glowing skin.